So next up on light, we have the photoelectric experiment, which looks something like this. Photoelectric experiment. And this is an experiment that showed that light must have particle properties. So we'll get onto that in a second. So first, what is a photoelectric experiment? Very simple. Light hits metal which releases electron. Okay? And we can even write it on here. So here's light. So any photoelectric experiment will have these same things. Light hits, it hits the metal. There's the metal. Metal, which releases electrons. So the electron comes out from here, and it goes through here. Electrons. And even greater than just having that sentence is being able to put it into an equation. Okay? Because light, the energy of the light is HF, and that equals the energy absorbed by the metal, W, plus the energy of the electron, which we measure. Like when I say energy of electron, it's how fast the electron is moving. So that's why we have kinetic energy at the bottom. Energy of the electron, and that's measured by our voltmeter. Okay. So after that, what else do we need to know? Theory, I'll get that in a second. We get a graph. This is usually what they want to give us, a graph of something like this. And the idea is, well, the idea of the voltmeter is that as we increase the voltage, so I'm going to draw another graph over here. As we increase the voltage, the current is going to go down. The number of electrons coming out is going to go down because we're pushing these electrons back. Like if you imagine heaps and heaps of electrons in here, some of them going fast, forwards, really quite fast, and some going really slow. If we put a battery that repels them, eventually some of these are just going to stop coming out. And that's why as we have no voltage going up, we have more current. But at a particular point, we have the battery up so high that none of these electrons can get away. And that's when we have zero current, and that's what this point is. And sometimes they may ask a question on this. But I digress. Let's get back to our graph. This is essentially the photoelectric graph. And on this side, when it says volts, this is kind of the volts required to stop the electron. So another way of thinking of this is the energy of the electron. It'll either be in volts or electron volts. Okay? So here's our graph, and really there's three things that you have to pay attention to that are probably the most important. And nearly every question will go through this. One, the gradient equals Planck's constant. So if we find the gradient of this, we can figure out Planck's constant. I'm just going to draw a line through it to get the work function now. Two, the threshold frequency is this. And three, the work function is this distance here. So that means if we look at our model up here, this 3 volts down here, 3 volts, we can convert it to electron volts in terms of energy. It means this piece of metal would absorb 3 electron volts before releasing an electron. Like if we started with 5 electron volts of our light, we send it in, it hits a metal, it absorbs 3 electron volts, and our electron is left with 2 electron volts. And that would be something that looks like this. Last thing I want to point out on this graph is that in this section, it's the negative electron energy. Does that make sense? You can't have a negative kinetic energy. It means the electron didn't even come out. No electron. Up here, it tells us the positive, how much energy the electron has. So if you think about it, all the experiments can only have points along here, and the rest of this is theoretical because we can't measure the negative energy of electron because it didn't even come out. Science is easy. Yeah, and so I put these points here. So most questions will ask you a variation on these themes. So here's the work function. Use the information above to identify the metal surface used in Sousa's and Peters' experiment. So they're telling us we have different metals. Which metal is this one? Well, I predicted, drawing the line, it's not a very good line, but maybe it should be better closer to here. Predicted the work function to be about 3 volts, or about 2.75 volts. So, according to this table, our metal must have been sodium. Okay. Next, use the results to calculate Planck constant. So just as I said, they're only going to use these 3 things. That one was the work function. Now they're going to find the gradient. So how do you find the gradient? To find the gradient, you need 2 points. Let's choose these 2 points because they're easier. Because remember, gradient equals rise over run. Keep it simple. And over here, how much did it rise? It rose 2 electron volts. And over here, how much did it go across? That's, what is this? That's 5 times 10 to the 14. So therefore, our gradient, Planck's constant, equals 2 electron volts over 5 times 10 to the 14. And that's going to give us Planck's constant in electron volts. But they may want it in joules. No, so that's okay. So let me try and calculate that. 2 divided by 5 is like 4 divided by 10. 15. Okay. So that would become 2 on 10 to the 14. 2 on 5 times 10 to the 14 equals 4 times 10 to the negative 15. You can do it in a calculator, which should be approximately our Planck's constant. Approximately. Yeah, in electron volts. So if you want to convert it to joules, you just have to use that conversion thing to get from electron volts to joules, which I believe is multiplied by the charge, which is times 1.6 times 10 to the something. And that's how you use the photoelectric experiment. I should be able to find another example. So here's another one. What is the minimum energy of your light foam that can eject an electron from the potassium metal? There's only 3 things they want you to do. The minimum energy is this point when an electron comes, so that would be the threshold frequency. So we can figure out here, we can get this frequency and then multiply by h to give us the amount of energy it has. Alternatively, we know for an electron to be ejected that HF has to be greater than the work function. So the minimum energy is when HF equals the work function, which is 1.8 electron volts. Okay. In terms of theory, the other kind of question they want to give you is this kind of thing: which would better describe the experiment was repeated with silver metal instead of potassium? The work function for silver metal is higher than the work function for potassium. So if it's higher, we know silver has to be lower because this work function for silver has to be bigger than that for potassium. So this looks like the right kind of graph. So it would be B. Things I want to point out is the gradient is always the same, so it cannot be D, it cannot be C, and then you just have to figure out which one of these two. Work function for silver is higher. Silver has to have a higher work function, which means it must be lower. Yeah. And now in terms of theory, I need to find a theory question. Well, you can stop now. It's up to you. I think there's a theory question back here.